All right, so in this video, we're going to show how we can compute the arc length or the length of a parametric curve. So similar to how we found the area under a parametric curve, we're going to start out with what we know about basically the Cartesian function counterpart. As in, if we're given a function like we start our mathematical journeys with, like y is a function of x, how we can compute the arc length for that function. So as we saw earlier in this course, if we have some function, y is a function of x, and we're interested in the arc length between 2 points, say x equals a and x equals b, we're interested in basically this length of this curve here. So we can set up an integral to do that. And the integral is from, well, point x equals a to the upper point x equals b of the square root of 1 plus that function's derivative squared, which in this case is f prime of x, capital F prime of x. And what I want us to recognize right away is this derivative of this function in the Cartesian form. We really think about this as a slope dy dx. The reason I bring that up is we're going to be able to do a mathematical sleight of hand in a moment where we introduce the slope for a parametric equation right there inside of the integral. So just to rewrite this integral, this is still in the Cartesian form, where we're considering y as a function of x. The integral from x equals a to x equals b of 1 plus, let's consider the derivative squared, or dy dx squared for that slope. And we're integrating still with respect to x. And now let's actually start shifting things around for our parametric curve. So this was our arc length formula for Cartesian functions that we derived a couple chapters ago. So remember, for parametric curves, if we're given some curve where x is a function of the parameter t and y is also a function of the parameter t, we knew how to calculate the slope. And the slope we still thought about as dy dx, basically a change in the vertical divided by a change in the horizontal. And we could write this in terms of those functions, x of t and y of t, or really a ratio of their derivatives. So the slope dy dx is equal to dy dt divided by dx dt. So we're going to take that slope that we just found and basically plug it into that integral. The other thing we can do is similar to what we did for calculating the area under a parametric curve. We need to change that dx into a dt because we want to integrate with respect to the parameter now. And we can do this a couple different ways. One of these ways that we can do this is we note that, well, x is equal to a function of t. Well, this might be a little bit obvious, but what if we, we take a derivative of both sides here? So really we have dx dt is equal to x prime of t. This doesn't really do anything. In fact, we could actually get rid of that right-hand side and rewrite that as dx dt. It's the same thing. And why would we want to do this? Well, we now have a dx in that numerator there, and we can go ahead and solve for dx in terms of that derivative that we have, the derivative of dx dt times dt. So we can actually take that and substitute it in for that dx up there. So let's go ahead and do that. I'm just going to keep the bounds open right now. So just draw kind of some circles to remind us that, hey, we still need to do this. We have the square root of 1 plus, well, that big old derivative squared now, which is looking like dy dt all over dx dt. When we substitute in that slope for a parametric curve, we are squaring that. And then we multiply on the outside by a dx dt times dt. And believe it or not, we are really close to having this full formula for the arc length or length of a parametric curve. The last step we're going to do is basically take this dx dt and bring it inside of this square root. So in fact, if we go ahead and do that, we still have this arc length where we're still unsure about those bounds. We have the square root now of, let me put in a couple parentheses here. We have that 1 plus that big slope formula that we had squared. But on the outside of those big parentheses, but still underneath, we will have a dx dt also squared. And then outside of that square root, we finally have that dt. So inside of that square root, we will have a dy dt that's squared in the numerator. And in the denominator, we will have a dx dt. You might be wondering, why am I highlighting that derivative or in that denominator? Well, when we actually take this dx dt and distribute it into those square brackets, we will see that that derivative in the denominator cancels out. So it turns out our arc length function or formula for a parametric curve can be written as the following. We're still wondering about those bounds, but it's equal to the formula of dx dt squared plus dy dt squared underneath the square root and integrating with respect to that parameter. And you might be wondering, well, at this point, how do we find those bounds? We find the bounds the same way we did for the area under a parametric curve. We go back to the curve itself and we say, I want to find the t value that lands me at this point. And we want to find the t value that lands us at that second point as well. And I think just for some notation, we said, you know what, let's call t equals alpha the t value that lands us at the point when x equals a. And let's call the value t equals beta the t value that lands us at that point along the curve when x is equal to b. So that is how we can compute the arc length along a parametric curve. So let's actually go ahead and do an example that involves that specific formula. And we're going to revisit our friend the cycloid to actually do this particular example. So we want to set up an integral that finds the length of one arc along the parametric curve given by this cycloid on the right-hand side. X is equal to t sine theta and y is equal to 1 minus cosine theta. So just so we're all clear, we want to find the length of one of these arches. So we want to start, say, at one point, and at the next time the arc or the curve touches the x-axis, and we're interested in finding the length of one of these arcs in general. So the first thing we need to do is figure out what t values land us at these specific points, and we can fill in all the details for the integral. So let's just see what we have in terms of the integral so far. So we know we have some lower t value, some upper t value that we need to find, and we need to substitute in those derivatives for the coordinate functions from our parametric curve. So right away, we can actually go ahead and compute those derivatives, dx dt, dy dt, just because we are given the actual equations for that parametric curve. So the derivative dx dt is equal to 1 minus cosine of t, and the derivative for y, dy dt, is equal to, in this case, what is this? Sine theta, or sine t, excuse me. So we basically know what's underneath that square root. What do we need to find? those values of t that land us at those specific points. So we want the value of t that lands us at these particular points because that defines one arc of our cycloid. And just like our previous video, at these points, we know x is equal, or sorry, we know at the first point, x is equal to 0 and y is equal to 0. At the second point, we know that y is equal to 0, and it's not as obvious what the corresponding value of x is there. So we can find the t values that land us along the curve such that y is equal to 0, or our points are going to be lying on the x-axis. So we take our y equation. Y is equal to 1 minus cosine of t. We set it equal to 0 because, again, that is the point that we care about. We know at both of these points, y is equal to 0 at these points because our point is sitting on the x-axis. And we can solve this equation. We get cosine of t is equal to 0, so we find a bunch of t values that work. T is equal to 0, plus or minus 2 pi, plus or minus 4 pi, and so on and so forth. And since this is a parametric curve, we know, well, the t values, if they're increasing, we're going to keep moving in the same direction along that curve. So we really only have to choose 2 successive t values to give us points at this specific value, at those specific points. So we can arbitrarily just say, you know what, I'm going to choose t equals 0 and t equals 2 pi. And if we find the corresponding x value when x is equal to 0, remember x is equal to t minus sine of t. So when x is 0, we will get 0 minus sine of 0, which means x is equal to 0 when t is 0. And when t is 2 pi, we get x of 2 pi is equal to 2 pi minus sine of 2 pi, which in this case says x is equal to 2 pi when t is 2 pi. So at the second point here, we also know that x is equal to 2 pi. But really what's important is we know that t is equal to 2 pi at this point. And at that first point, we know t is equal to 0. So we do actually have bounds now for our integral. So let's put all of this together. Our arc length integral then rolls from t equals 0 to t equals 2 pi. We take the square root. We'll square both of these terms, so we have the derivative dx dt. So that derivative is 1 minus cosine of t. And we add to that, after squaring it, the derivative of sine of t. And of course, we square that as well, dt. So this problem basically told us to set up an integral to compute the arc length here. And if that was the problem, set up the integral, we are done if it's just to set up the integral. But I feel like going rogue a little bit and just computing this integral for fun. So let me just get rid of this extra cycloid I had at the bottom here. And let's go ahead and just compute this integral, just for some practice. So underneath that square root, if we simplify, we'll get 1 minus 2 cosine of t plus cosine squared of t plus sine squared of t. And well, this is looking like it could be a real big mess for us. But this is where knowing some trig identities can actually really help us out. So for example, we know that sine squared plus cosine squared is equal to 1. So that whole thing, we can change into just a 1. So this integral becomes the integral between t equals 0 and t equals 2 pi of the square root now of 1 minus 2 cosine of t plus that 1 coming from our trig identity. Well, we can actually clean this up just a little bit more. We can combine both of those 1s underneath that square root. So we get 2 minus 2 cosine of t. And in fact, we could factor out a factor of 2. So we get 2 times the quantity, 1 minus cosine of t. Well, this is still looking like a, I don't know about you, a pretty difficult integral. And in fact, we can actually use some trig identities to help us out here. So let's do a quick aside for a moment. And this is a non-obvious trig identity. Read between the lines. This is not a trig identity I'll expect you to whip up on a test. But remember, we have our half angle identities. So if we had something like sine squared of theta, this would be equal to 1/2 times 1 minus cosine of 2 theta. Well, we don't quite have this. We have a 1 minus cosine type thing, but we don't have 1 minus just a cosine of theta anywhere. I'm going to keep moseying along with this. I'm going to multiply this 2 over to the other side. So we have 2 sine squared theta is equal to now 1 minus cosine of 2 theta. And notice this sleight of hand. Well, I'm not going to consider this as a 2 cosine. I want this to be a t because that is what we have over here. What that means though is if this was a 2 cos or 2 theta, we'd have to change this other theta accordingly. So if we're going from a t or a 2 theta to a theta, we need to go from a t to a t over 2. So this trig identity we can actually use is 2 times the sine squared of t over 2 is equal to 1 minus cosine of t. And this is actually a pretty slick little playing around with trig identities, because what's going to happen when we take a square root of something squared? We get rid of that square root rather cleanly. So the next move we're going to make is actually substituting 1 minus cosine of t in for, or sorry, this 2 sine squared of t over 2 in for 1 minus cosine of t. So we have this is 2 times 2 sine squared of t over 2. dt. And well, what's particularly nice about this even is we have 2 2's, so we'll get a factor of 2 squared under that square root. Square root will also knock down one of those powers of 2. So we're just going to get a 2 out of this. So the square root is basically going to turn into, the integrand is going to turn into just 2 times sine of t over 2. And we're integrating with respect to dt. And this is a much easier integrand for us to actually compute now. So going ahead and computing this integrand, we have that factor of 2, or the integrand's antiderivative. We still have that factor of 2 out in front. We have a sign that's a positive sign, so we need a negative cosine coming from the antiderivative. And we need that divided by a 1/2 coming from the chain rule. So we have a 2 times a minus 1 coming from the antiderivative of sine going into negative cosine of t over 2. But then we also need this is divided by a factor of 1/2. And let's not forget that we get to evaluate this at t equals 0 to t equals 2 as our integration bounds. So the length in this case will be equal to minus 4 times the cosine of t over 2 between 0 and 2 pi. So let's go ahead and put those values in. So the length is equal to, let's evaluate at the upper bound, minus 4 cosine of 2 pi over 2. We subtract a negative quantity at the lower bound. So a negative negative will turn into a plus. And we have 4 cosine of, well, this will just be 0. So let's see what this turns into. Cosine of 0 is 1. So we get a positive 4 from that second term. This first term, in that numerator or in that cosine, we will just get a cosine of pi after the 2's cancel out, which is negative. So we have a negative 1 times negative 4. That gives us a 4 as well, because cosine of pi is a negative 1. So the length of this curve is actually equal to 4 plus 4, or 8. So that is the length of one arc along this particular cycloid. But remember, what's important for us is that we were able to take that arc length formula for Cartesian functions, y is a function of x, and we converted that into the parametric curve analog, where we had that the arc length integral for parametric curves is an integral between some starting t value, some ending t value of the square roots of each of those coordinate functions squared dt.